Hello and welcome to this video where we take a look at how we can simulate the McCabe-Thiele method in Python. So what we're looking at is a problem where we have a benzene toluene mixture containing 42% benzene, and it's to be separated into benzene and toluene. And what we want is we want one flow with 70% benzene and the other with 10%, and these are all in mole percentage. We're assuming a reflux ratio of 1.5, and we need to figure out how many column we need if the feed contains of 75% vapor and 25% liquid. We also need to know what the optimum feed location is, and the extra data we've been given is the mole fractions of the benzene toluene mixture. So first of all, we're going to solve a problem that's a little bit different from what's been given here, just to make our calculations a little bit easier. First of all, what I'm going to do is, instead of having a curve that's drawn using these equilibrium points, what we're actually going to do is we're going to assume an equilibrium curve of this particular equation where y equals alpha times x over 1 plus alpha minus 1. Here, x and y are the coordinates of the vapor and liquid fractions. However, alpha is actually the separation factor. So let's take a look at how we'll do that in Python. First of all, you can already see I've done some imports. I've imported matplotlib.pyplot as PLT. For most of the videos that I've done, we've used Plotly, but this time we're going to use the matplotlib. Similarly, we're also going to import numpy as np to make our calculations easier. So first of all, there are also some different starting conditions in the problem that I'm going to solve. We're going to assume that the feed has 35% of our light component, and then we want our distillate to have 97.5% of our light component, and our bottoms can have the 2.5%. Likewise, we have the reflux ratio of 1.5. We're assuming a separation factor of 2.5, and our Q, which is our feed condition, is going to be 1.5. So first of all, let's write our equilibrium curve in Python. So I'll define the curve as EQ, and first of all, our x values should be a bunch of random values from 0 to 1. So let's say np.linspace 0, 1, and I'll make 51 equally spaced values. The reason I go from 0 to 1 is because those are the mole fractions. Mole fractions go from 0 to 1. It can be lower, it can be any higher. Similarly, our y value is now going to be according to the equation that we have right here. So that's the separation factor times x divided by 1 plus x multiplied by our separation factor minus 1. So those are going to be our x and y values, and we're going to return x and y. One thing we've noticed is that this function does need an input, and that's going to be our separation factor. So let's put that in right there. We've got that, and once we've done that, let's create two variables which will actually take the x and y values of our equilibrium curve. So that will, I'll call the x coordinates x underscore EQ, and our y coordinates would be y underscore EQ. There we go. And here I'll just pass in the function. So that's going to be our EQ, and we give it A. So there you go. That's our equilibrium curve. Let's take a look at all our values. Our xEQ, yep, simply 0 to 1. And our YEQ will be calculated for every single one of these values. And there's our array of y values. So now we have our equilibrium curve. So next thing we want to do is we want to know the equation of our Q line. Good thing for us, we already know what that is. So Q line is always equal to Q over Q minus 1 times X minus XF divided by Q minus 1. So we can write this equation as is. However, we don't know where x and y, the actual values of x and y. So what instead we're going to do is we're going to use this equation, the equation of our q line, and equate that to our equilibrium curve. So what I'm trying to do here is that for our q line, which is this blue line right here, we already know one of the coordinates, which is going to be the feed composition. So xf comma xf, that's going to be our first coordinate of the q line. Now we don't know the second coordinate, so what we're going to do is we're going to extend this blue line all the way to our equilibrium point, and we can see that it will intersect there as well. So by equating these two equations, the equation of equilibrium curve and the q line, we can find at which point it'll intersect, and using those 2 points we can find the actual coordinates of every single point in that q line. So by equating these two equations, we get this particular equation, which is x squared times q times separation factor minus 1 and all of this thing. So let's write a function that will actually calculate this for us. So I'm going to define a new function. So define, let's call it q line. I don't know what everything that's going to be used as an input, so I'll just leave it blank. So what I'm going to do is, instead of calculating this whole thing, I will calculate the 3 coefficients of this quadratic functions, because as you can see here, there's x squared, x, and our constant xf. So let's calculate our coordinates. So our first coordinate is going to be q times alpha minus 1. So let's write that. So let's call that c1 equals q times our separation factor of minus 1. And then we have our second coordinate, which is going to be this long thing. So I'm just going to write that down one by one. So q plus xf times separation factor minus 1 minus separation factor times q minus 1. Yeah, there we go. And finally, we have our third coordinate, c3, which is going to be our negative xf. So negative xf, the mole fraction of our light component in our feed. So there we have them. And after this, what I'm going to do is I'll just make an array of all of these coordinates, all of these coefficients. So let's call them COEFF equals C1, C2, C3. Oh, there's supposed to be commas. Got that. And then what I'm going to do is what we want to do from here is, using these coefficients, we want to find out the root of this function. When we find the root of this equation, we're going to find the actual x coordinate of the intersection between the q line and the equilibrium curve. So in order to do that, what I'm going to do is, let's call this roots equals np dot roots of our function COEFF. So what this function does, it just takes these 3 coordinates, turns this into a quadratic function, and then finds the root of that function. Once we have the roots, just to make things easier, I'm also going to organize the roots. So I'll go np.sort. The roots will be calculated and then sorted in an ascending order, just to make future calculations easier. So now we have this. Since we have a quadratic equation, we're going to have 2 roots. But we know that by visually we can see that the 2 lines, the equilibrium curve and the q line, is only going to intersect at 1 point. So most likely what might happen is the lines will intersect such that the roots we will have one positive root and a negative root. In case we get both positive roots, we're just going to go with the smaller root. So what I'm going to do here is say that if roots and the first value in the roots variable is greater than 0, then I'm going to say that so x intersection, what shall I say? Actually, let's call it x intersection of q line is equal to roots 0. That means if the first value is not negative, then we're just going to say that that is the intersection point. Now, if that is false, or else, which means the first value is negative, then our intersection point is just going to be roots and the second number in this array. So I've got that. Now, what we have is the x coordinate of this intersection and x and y coordinates of this section. What we actually need is an array of values that will represent points, all the points in the Q line. So what I'm going to do here is make an array of values of all the x coordinates. So what I'll do is I'll take x coordinates from the feed composition all the way up to the intersection. So that will be, let's call it x underscore eq, because x underscore q, because those are the x coordinates of the q line, and they are calculated as np.linspace. There's a bracket there by accident. So linspace, and we want to go from our x intersection all the way to xf, which is the feed conditions. And then let's say I just want 51 equally spaced values. I've got that. And then the y coordinates of our q line will be calculated using this particular equation right here. So that would be q times x underscore q divided by q minus 1. And then we have minus xf divided by q minus 1. And there we go. These two arrays can represent all the points in the q line. So let's return x underscore q and y underscore q. And what I'd also like to do here is bring these store the two values in two variables. So x underscore q and y underscore q. And they will be obtained from q underscore line that take inputs. Okay, so our inputs here, I forgot to do that. So first of all, our input will be the separation factor, and then xf. And let's see if there's anything else. Yeah, and we also need q actually. So we have a, xf, and q. So let's send it here as well. A, xf, and q. Let's turn that into a comma, and there we go. So let's take a look at what values we get. Our xq is all of these values, and our yq would be all of these values.